Hi, I'm Aki Fujimura, CEO of D2S. D2S is the managing company sponsor of the eBeam initiative, and eBeam initiative welcomes today Dr. Harry Levinson. Harry really needs no introduction. He's got 4 decades of contributions, significant contributions to the world of semiconductor manufacturing and links from design to manufacturing, particularly through the eyes of lithography. So it's really, we are very fortunate to hear from Harry today, his impressions from the recently concluded Photomask Technology and EUV Lithography Conference. Harry?
Thank you for the introduction, Aki. Hello. This year at the Photomask Technology and EUV Lithography Conferences, we were again treated and able to hear about new and exciting developments in EUV lithography and photomask technology. As typical for SPIE lithography conferences, much of the material that was presented consisted of the results of recent research and development. This year, however, we began to see presentations that addressed more manufacturing-oriented issues, reflecting the first use of EUV lithography in high-volume manufacturing just last year. We were informed that there are now 62 full-field 0.33 NA EUV exposure tools operational in wafer fabs around the world. This is really a remarkable number. For that tool set, on average, they have 84% availability. While this isn't quite what we'd like to have in high-volume manufacturing, it's not inconsistent with the level of reliability that we had seen when we were introducing other new generations of lithographic technology, such as KRF lithography and ARF immersion lithography. Today, ASML is no longer focusing just on trying to establish fundamental capability for EUV lithography, but they're working on incremental improvements and introducing new models. There are other groups around the world that are also working on trying to make improvements to EUV lithography in order to enable high volume manufacturing and make it better. For example, we saw papers on improving the venerable molybdenum silicon multilayer that we use for reflectors on our masks. There's an interesting paper that involved bulge testing pellicles in commercially available reticle pots. So here was testing in a true manufacturing setting. There was an interesting paper from Rick Yonkir of IMEC who looked at chemical contamination on EUV masks over the course of exposure and as the reticles were taken in and out of the exposure tools and kept in storage. And indeed, subtle variations in critical dimensions were seen, the type of thing that's important in high volume manufacturing. There was another paper from IMEC that looked at CD variation across the slit due to flare from neighboring fields. A small effect, but again, the type of thing of importance in high volume manufacturing. There have been a lot of papers in recent years on EUV pellicles, and this year was no exception. We saw that polysilicon pellicles now have transmission as high as 88%. Other materials were, other potential EUV pellicle materials were discussed. There was a paper on using silicon nitride coatings on polysilicon. There's also one paper discussing the use of molybdenum disilicide as the fundamental material, and there was more discussion of carbon nanotubes for EUV pellicles. Although EUV lithography is in high volume manufacturing, there were quite a few papers from universities and research laboratories in Asia, Europe, and the United States, and they covered a wide range of topics. They gave papers on new absorber materials to address mask 3D effects, several papers on resists and resist processes. There was a paper on free electron lasers, mask heating effects, computational methods, and quite a few people presented on metrology for EUV lithography. Several papers had data that were taken using imaging systems at either the Paul Scherrer Institute in Switzerland or Lawrence Berkeley National Laboratory in the United States. These are tools set up in laboratory environments that are allowing people to look for a very fine patterning of resists and try to make sure the resists will be ready as needed when we get to more advanced nodes. Resists have indeed been a limitation for EUV lithography for quite a long time, but we saw some encouraging new results. A lot of the data involved line space patterns below 30 nanometer pitch. This included material involving chemically amplified resists, but there are also a couple presentations on resists involving a very different mechanism, namely that of scissioning. Several people talked about the very fundamental mechanisms behind stochastics-induced defects, very critical for the advancement of EUV lithography. And all this work was oriented towards moving forward to future advanced nodes. In that regard, ASML and ZEISS have done really a remarkable job in bringing along high-NA EUV lithography capability. For example, the engineers have, it was reported that the engineers have achieved 4 times the acceleration for the reticle stage on the high-NA tool as they had previously. And that's pretty remarkable considering the acceleration was already pretty good to start with. The optics being made by ZEISS are very large. Nevertheless, the key characteristics such as surface figure and roughness are quite good. There are some changes we need to be making in our technology as we go to high NA. For example, no longer is it suitable for using Zernike polynomials to characterize aberrations, and there's some discussion of the new type of polynomial we referred to as Todians. Also, with high NA, to make large area devices, we're going to need to do stitching, and there was a paper talking about some of the details of what will be necessary to enable that. New mask architectures and the computational lithography needed to support that will also be important, and there were some very nice papers presented on those topics as well. The conferences weren't all about EUV lithography. There was also quite a bit at the Photomask Technology Conference on optical lithography. So, for example, there were several papers that discussed the application of deep learning to improving mask making. And several presenters also talked about having curvilinear features on masks. One of the key enablers for that, of course, is a multi-beam mask writer that makes it much easier to make these features. And there was a presentation on a new multi-beam mask writer. But we also heard from D2S a way to make curvilinear features more efficiently using vector-shaped beam tools. On the EDA side, there were papers on mask process corrections and mask rule checks in support of curvilinear features. Interestingly, in the survey results presented by Jan Willis, the Luminaries survey, the majority of luminaries felt that both deep learning and curvilinear features will be important in the near future. In the mask survey results presented by Aki Fujimura, it was interesting to note that most of the masks still being made are for older nodes, 130 nanometer and older. And that's in spite of the fact that going from 2019 to 2020, there's been pretty much a doubling in the number of masks being made with these new multi-beam mask writers. Missing from this year's conference were the informal and social interactions that have long been an important part of the Photomask and EUV conferences. I'm hopeful that next year we will again be able to have the pleasure of face-to-face interactions and discussions on lithography and enjoy some good California wine in Monterey. Thank you.